Now, 7. This is now we are going to test the slope of the equation. Well, we set up the null hypothesis that B, the actual slope of the equation, is equal to 0. Translation, the linear model that we have chosen is not significant. All right, meaning defect rate and batch size are not correlated. The alternate hypothesis would say that the slope, the actual slope of the equation, is not equal to 0. Translation, the linear model is significant. Translation, the defect rate and batch size are correlated. All right? So we learned from the 2 previous problems we did that we can render a conclusion on these hypotheses by simply looking at the p-value associated with the slope of the predictor variable. Now look at the p-value there. So when you see this 3.5e minus 20, this is actually where the p-value is expressed in exponential form. So if you want to convert this into decimals, you can highlight those cells and then select format cells and then select number and change the decimal places to, and in this case, you'll have 20 zeros before you get an actual number. So we can just leave it as maybe 6 decimal places. And here you go. Look at the p-value associated with the slope, right? Let's go back here, and we will say that the decision rule to reject the null hypothesis if p-value is less than alpha. And we know that the p-value is quite small. Regardless of the size of your alpha, you will reject the null hypothesis. So the interpretation or the decision that we will make here is that we will conclude that the linear model is significant. Okay, so again, we're going back to this model. We're testing the model for significance. So we can see that in this plot. Look at the, tight sort of a correlation between batch size and defect rate. But just because a model is significant does not necessarily mean that you can use that model for prediction at this point. Okay, there's one more step that we have to carry out, and that is testing or answering the question, is the linear model appropriate for this data? Okay, and how do we do this test? Well, we look at the analysis of residuals. So using the residual plots, and let me move the residual plots that I generated earlier. Okay, so these were the plots that were generated when I run the regression. All right, let's go back to one of the problems we did last week. Okay, when we looked at the analysis of residuals, we will conclude that a particular chosen model, in this case, linear model, is appropriate if, 1, there is no pattern in the residual plot, and 2, that the normal probability plot is approximately linear. And I'll copy these two so I don't have to go back here every time. Let's go down here. So if you look at the batch size residual plot, is there no pattern in this plot here? Or is there a pattern?
I think there's a pattern.
There's a pattern, exactly. There's an obvious pattern in in the plot, and it's sort of U-shaped. All right. How about the normal probability plot? Is it approximately linear?
Yeah.
Yep. All right. But because this is violated, then we will conclude. So, if one or the other, meaning either number one or number two or both are violated, then now we will conclude this. The linear model is not appropriate. So if the linear model is not appropriate, we cannot at this point use the linear equation in estimating the defect rate that will be produced by a given batch size. All right, not yet at this point, because what this tells us that the linear model is not appropriate. What this tells us is that there is a better model that will represent the relationship between defects and batch size. And what was it that we observed in the plot? We tried to fit a linear model there. Yeah, that linear model is significant, has a high correlation value, has a very high R-squared value, but the linear model does not fit. Okay, so what model appears to be a better fit? Well, we observed that to be more curved. So let's go back to this scatter plot, and let me recreate another scatter plot side by side so we can do a side-by-side comparison. Highlight these two columns, insert XY and this. Okay, and I'm not going to create the include titles. Okay, click on any of the data points, right click, add a trend line, and instead of linear, let us see if exponential would be a better fit. Does that look better? Probably, but then you will note here that as x gets bigger, the curve will go higher, but so you'll have huge errors in your forecast, especially when you extrapolate your data. Let's look at logarithmic. No, definitely does not fit, right? How about tower? Oh, looks better. Probably more fit, right? Or let's look at polynomial. That also fits better, doesn't it? Okay, so let's select polynomial, and then we're going to display the equation on the chart. Here it is. And we are also going to ask Excel to display the R-squared on the chart. Now, compared to the linear model, look at the R-squared value of the of this. Well, this is a quadratic model. Okay, it takes this form. Y is equal to A plus BX plus CX squared. Okay, this is known as, you probably have seen this in your high school algebra. This is known as the quadratic model. And in the quadratic model, you have two predictor variables. X, one of them is X, and the other one is X squared. So, we are going to, once again, rerun the regression equation using the quadratic model. I have recreated the original or copied the original data set where you have X and Y. So this is Y, and you have two predictor variables: the original variable batch size and batch size squared. So the column C here was computed based on the squares of these numbers. Okay, so you see that there's a formula in cell C4, and that is B4, which is 100, and then square that value. So that's the revised, well, we'll just call this the revised data for generating the quadratic model. So we'll go back to here. We are going to generate the regression equation, and this time using the quadratic model. And then we will answer questions 5 and through 11 again, using this quadratic model. All right, so we will select data analysis, regression. The input Y range would be defects, and the input X range will be batch size and batch squared columns. Okay, you have to make sure that the independent variables are in adjacent columns. We'll select still labels. The output range, let's put the output somewhere here. Output range, let's start that in E3. And once again, we're going to generate the residual plots and the normal probability plot for the test of appropriateness. Then click OK. So here are the residual plots that were generated by Excel. I'm going to remove the grid line, so the worksheet will be a little bit cleaner. Grid lines. All right. Now, let me copy the same questions we asked in the previous model. Okay. So, question number 4, it says, what is the regression equation? The regression equation follows this model. Y is equal to A plus BX plus CX squared. The quadratic model that we said would be at least follows the plot. From the output, we're going to pick up the value of A. This is A. Here's B, and here's C. Again, this would be A, this would be B, and this would be C. So to build the regression equation, we will say that Y, number of defectives produced, is equal to 6.89 minus, Y minus, look at the slope of this coefficient, it's a negative value, minus 0.1201 batch or X plus 0.00095 batch squared. So this is what we call as the quadratic model. So what is the correlation coefficient for this quadratic model? Here you go. The R value of the quadratic model is 0.9977. Is this a better number than the linear model? Here's the R value of that model, 0.9764. So which one is better in terms of the R value? The linear model or the quadratic model?
Yeah, it'd be the quadratic model.
Correct. All right. How about number 6? How much variation in the response variable can be explained by the independent variable? So looking at the output, the R squared value is this. All right, I'm converting it to percent now. So it is 99.54. The R squared for the linear model was only 95.3, but the quadratic model is even better at 99.5. So by these measures, the R and the R squared value, the quadratic model, is a better model. Is the slope of the regression equation significantly different from 0 at a significance level of 0.5? Now for number 7, we will need to modify this a little bit because in the quadratic model, there are 2 coefficients that need to be tested. Right? So that now we're kind of leading to the next chapter, which is multiple regression. We define the difference between simple regression and multiple regression models. We said that if there is only one X or only one predictor variable in a model, it is simple regression. But in this quadratic model, how many predictor variables do you see?
2.
2, correct. So there are 2 predictor variables. Therefore, this is what we call as a multiple regression model. Okay, so because there are 2 predictor variables in multiple regression, when we do this question, is the slope of the regression equation significantly different from 0? We can actually revise this to say that are the coefficients of the independent variables all equal to 0? Okay, so the translation of for testing the hypothesis, we'll say H sub 0, the coefficient of variable 1 is equal to the coefficient of variable 2, predictor variable 2, and both of them are equal to 0. Okay, this is known when you read chapter 14, this is known as the global test. So the interpretation of the null hypothesis is this: the multiple regression model is not significant. Right? H1, the alternate hypothesis, would say that at least 1B is different from 0. Translation: the multiple regression model is significant. So we will still reject HO if the p-value is less than alpha. So the question is, which p-value? Where are we going to obtain this number from? Recall that there are 2 independent variables in the output over here, and we will pick up the p-value associated with those 2. So I'll change this to number. And all right, so look at the p-value associated with batch size. It's almost 0. Look at the p-value associated with batch size squared. It too is almost 0, or both of them are less than the significance level of either 0.01 or 0.05. So we will conclude here that the multiple linear model, or actually we can just call it quadratic model, is significant. So let's skip down here. Is the quadratic model appropriate for the data? Again, looking at the residual plots, let me copy these plots and move them down here. Okay, so the first plot is batch size and the first predictor variable, right? Do you observe any pattern here? Or is it pretty much random? So this one pretty much random, right? There's no obvious pattern. How about batch size squared? Also no pattern. So that's good. We don't observe any pattern in the residual plot of both predictor variables. How about the normal probability plot? Is it approximately linear? The answer is yes. Because both of these are satisfied, then we will conclude that the quadratic model is appropriate, reflected in the scatter plot we generated earlier over here. Let me copy this to the worksheet. You will note that the quadratic model fits quite well within the data set. Because of this, then we can use the model for estimation. So just to kind of summarize, number 11 really is the reason why we perform regression and correlation analysis. And that is we use a model for predicting or estimating the value of a response variable or a variable of interest. We should use a model if and only if, or if only when a model goes through these steps and the model is determined to be significant, and in addition to being significant, we would want that model to be appropriate. So the question is, why would we not use the linear model as a way to predict or to estimate defect rate? Why would we not use, or why shouldn't we use this model for estimating defects given a batch size? Here's the answer. One is that if you use a model that is not appropriate, here's a potential problem for this model. Okay, we know that the behavior of the data is curved, right? If we use a linear model for estimating the defect rate given a batch size, so let me extend this dashed line going this way, meaning if we extrapolate, when we extrapolate, we go beyond the relevant range of data. What is it that you observe that will happen to the prediction error? What is it that you see in this plot here?
I think if we use that one, when it got to like that, what?
Yeah. Go ahead. If we use the linear model, what happens when we extrapolate?
Like when it gets to higher numbers, it won't be correct.
But if we force a linear model to that and use that linear model for extrapolating, meaning going beyond the relevant range of data, what is it that you observe in terms of the difference between the predicted y, so y hat? So any point on this line would be your y hat. What would be the difference between y and y hat? So this is the error.
It would be, the actual number would be higher than the predicted one.
Correct. But if you look at the thing here, that the error gets bigger and bigger, right?
Yeah.
When predicting, you would want the difference between the actual value and the forecast. And within the relevant range of data, that will not be much of a problem. But when you try to extrapolate from your data, then the error becomes much larger. Secondly, if the model is not appropriate, that tells you that, hey, maybe there's a better model. So when you have a better model, and as we see in this quadratic model, this model is better in terms of the R value, the R squared value, and is more appropriate. So for predicting purposes, if you say that this dashed line that you see in this plot, the dashed line represents the forecast or the predicted value of y given x, that your error in prediction would be much smaller than using a model that is not as appropriate. Here's now the question. We have determined that the quadratic model is appropriate, therefore we can use it for estimation. For a batch size of say 250, batch size or X of 250, what is the expected number of defective shafts that will be produced? Okay, so again, let's say that you're the manager of this production outfit, and you decided to run a batch size of 250. Question is, how many of these 250 will be defective? Let me copy the quadratic model. So how would you answer that question?
So would you have to put the batch size into the formula for where it says
Okay.
batch?
Okay, so tell me how I will do it. Here's the model.
Y equals 6.89 minus 0.1201.
Okay, hold on. 0.1201. Okay,
And then like times 250 for parentheses
correct.
plus 0.00095
Correct.
250 squared.
Correct. 250 squared. I'm missing a 2 there. So anytime you put like a caret, that's like raised to the power 2. So here it says that for a batch size of 250, the expected number of defective shafts is around 36 units. So that's, now I'm using this model for estimation. Now, what if we produce a batch size of 300? Well, we'll have to edit this formula and replace this with 300. Now, a better way of making cell N86 compute automatically when N82 or the value in N83 changes is that instead of typing in the constants there, let's just replace that with the cell location of the value of X. Same thing here. Instead of 250, we will replace that with the cell location of the value of X. So there you go. So 56. If I say how many units, defective units will be produced if I have a batch size of 400? There you go.